Welcome to Dallas and to SC22. I'm Rupak Biswas from NASA Ames Research Center and the SC22 Lecture and Plenaries Chair. I'm excited to kick things off tonight with our HPC Accelerates panel session. I'd like to introduce our panel moderator, Addison Snell. Addison is a veteran of the high-performance computing industry and co-founder and CEO of Intersect 360 Research, now in its 15th year, delivering forecasts and insights for high-performance markets. Please welcome Addison on stage to lead the panel discussion.
Hey, Addison. Thank you.
Good afternoon. I'm Addison Snell with Intersect 360 Research, and I am absolutely thrilled to be here at SC22 in Dallas, and even more thrilled to be invited by the SC22 committee to be the moderator of this opening HPC Accelerates plenary panel session on the many dimensions of HPC acceleration. I'm especially excited for the diversity of the expertise of the panelists involved who are going to be able to talk about multiple dimensions of HPC, multiple dimensions of acceleration. We're really looking forward to having a fun time up here. Thank you for being in attendance, and please join me in welcoming my panelists. Jim Cherry is the Associate Director and Chief of Research Technologies at the National Institute of Allergy and Infectious Disease, or NIAID. Thomas Schulthess is the Director of Swiss National Supercomputing Center, CSCS, and also professional for computational physics at ETH Zurich. Shubho Sengupta is an AI researcher for Meta in the Fundamental AI Research Group, or FAIR, and Gina Tourassi is the Director of National Center for Computational Sciences at Oak Ridge National Laboratory, the home of the exascale Frontier supercomputer. Please join me in welcoming our panelists. Thank you very much, everybody. And as we said, the theme for SC22 is HPC Accelerates. We're here talking about the many dimensions of HPC acceleration. As I was saying in the introductions, you come from a lot of different types of organizations up here. I'm really looking forward to the conversation. Why don't we just start by giving a quick introduction of yourself, your role, and your organization. And Gina, I think people have heard of Oak Ridge National Labs at this point, but I'll start down at the end with you and what you're doing at ORNL and the Department of Energy Office of Science.
Absolutely. The Oak Ridge Leadership Computing Facility is part of the DOE complex. As a leadership computing facility dedicated to open science, our primary mission is to deliver compute and data infrastructures that are world-leading to enable our user community, which are researchers across the world, tackle some of the most computationally intensive and most timely scientific challenges. What is important to emphasize is that we serve a very diverse community of researchers, researchers from academia, from industry, from national labs, and of course from federal agencies. And we also serve very diverse scientific domains, because as I say, in the 21st century, pretty much every scientific domain is computational.
All right, thank you, Gina. And Shubho, just as I was saying, this crowd has mostly heard of Oak Ridge National Laboratories. I'm pretty sure they've all also heard of Facebook. Why don't you introduce yourself and Meta, but particularly with the Fundamental AI Research Group, or FAIR.
Hi, thanks for having me here. I'm Shubho. I've been at Meta for a little over 5 years. I work in the Fundamental AI Research Lab inside of Meta. FAIR itself has existed, I think, around 9 years or so. We are very much of an academic lab, so to speak, inside of Meta, and our goal is to further AI research. And the reason I think, one of the reasons I'm here is AI is a big driver of compute these days. So just to further our own research, to shorten our experiment cycles, just for research, we run some of the largest compute infrastructures in the world. And we work with pretty much any domain inside of AI, be it language, vision, speech, reinforcement learning, robotics. And we have collaborations with academia as well, pretty much around the globe. So we serve also a pretty diverse set of customers, though within the AI space inside of FAIR.
And Thomas, you're also with the National Supercomputing Center, but with a close tie to academics at ETH Zurich or ETH Zurich.
Yeah, so we are, our mission at CSCS is to develop and operate high-performance computing and data research infrastructure to support world-class science in Switzerland. We are part of ETH Zurich, which is one of the leading engineering schools in Europe. So science is very broad, goes from traditional physical sciences, life sciences, including medical sciences, all the way to things that are supported with AI today. And we are also, and that maybe distinguishes us from some of the similar facilities in other countries, we operate or develop and operate a numerical weather prediction system for the National Weather Service of Switzerland, Meteo Suisse. So high-performance computing and data covers everything from fundamental science all the way to the applied sciences in the earth science sector, mostly.
Now, Jim, talk about important organizations. If this had been a couple years ago, I don't know how many of everybody would really be familiar with NIAID, but I think over the last couple years, the profile's come up a little bit, but still, why don't you talk about what you're doing there?
Sure, yeah. So first I want to thank everyone for allowing me to be here. And I think I'm a little different than my colleagues here on the panel stage here, because I'm a biomedical scientist, and my role at NIAID is to provide cutting-edge research technologies, anything from digital spatial profiling to single cell to bulk RNA-seq, cryo-EM, confocal microscopy, and that data being able to not only be transported across the country, because NIAID does have laboratories out at Rocky Mountain Laboratory, so 3,000 miles back to Bethesda, to be able to apply it to the clinical center there at the NIH. So we play a big role in working very closely with the basic researchers, but we really see ourselves more as a group that is the bridge between basic research and clinical application. And to do that, we need this high-performance computational, and to accelerate that type of work being done.
Well, that's a great transition to the first big topic, because we're talking about this theme is HPC Accelerates, the many dimensions of HPC Accelerates. Now, there's literal acceleration, I suppose, of computation makes the application run faster, but beyond that, are we accelerating scientific discovery? Are we accelerating human endeavor? There are a lot of lofty things we can accelerate. So when you look at this tagline, HPC Accelerates, in the context of your organization, how do you each think of that? What is it you're accelerating? I'll start down at the end with Gina again.
Well, you summarized it well. First and foremost, when you strive to be at the bleeding edge of high-performance computing, the ultimate goal is to accelerate computation for some most pressing and challenging problems, right? But why do we do that? Because we want to accelerate scientific discovery within specific domains. And ultimately, we want to accelerate innovation and bring to bear solutions for problems that are very important to humanity. And certainly over the past few years, we have all experienced all the existential threats that humanity faces, starting from climate change, resource scarcity, and pandemics. And when you think about what we have faced as a society in the past 3 years, all of these threats acting together, you realize how we need to bring these resources and accelerate innovation even faster. Innovation in terms of better predictive models for climate and extreme weather events, or better predictive models and management for diseases, new materials that are sustainable, and renewable energy sources. All of these activities, the way I see it, require deeper understanding of complex systems, right? Is it physical systems? Is it biological systems, ecological systems, social systems? And HPC always has been at the core of helping us understand, model, and understand these systems and their interactions. So we hope that we will continue to innovate in this particular space and will accelerate even more because, honestly, I feel that we're running out of time with many of these challenges.
That's a really interesting point. We're going to be able to talk about that more and the importance of acceleration. Thomas, I want to come down to you next. How do you think of this HPC Accelerates theme with respect to CSCS?
So HPC being scientific computing or rooted in scientific computing, it definitely accelerates science. And as science is probably advancing, digitalization has been. We can go to CERN, we can go to earth sciences. Digitalization in society, in pretty much all fields that modern science touches. As we are advancing digitalization, the importance of scientific computing, statistics, data analysis, sometimes called data science these days, applied statistics, and these things, so you learn how to accelerate these things in science, and they touch any domain in science, so they are not limited to anything in physical sciences, it's in life sciences, it's in social sciences, it's everywhere. So we learn it in basic science and we apply it to things that matter in society, and that's how we end up covering everything. We are often called, a national supercomputing center. Maybe from the past where HPC is coming from, there is always a national pride behind it. And we sometimes deal with metrics that are a little bit off or become a fetish in itself. But the really important part is that we are advancing really applied problems in society and in the economy. We are part of a teaching enterprise, education enterprise. And I think in the end, we accelerate more than just computing. We accelerate, like you said, innovation and how society is dealing with the problems it has to deal with today.
And just to add a couple things to that. So, I know the last 3 years we've all been through a lot, right? This pandemic. But I will tell you, and it's something I was talking to my colleague Gina earlier about. So in HHS, we too have a national lab called the Frederick National Laboratory for Cancer Research. It's located in Frederick, Maryland. And during this COVID pandemic, it really gave us an opportunity to see, and how do we say it, Gina, collaborations, strong collaborations. And we saw this across all the different divisions, offices, and centers, from the NIH to the clinical center, to CDC, to the FDA, and then ability with authorities that we have from Congress at the Frederick National Lab, or they have at the Frederick National Lab, to be able to put together these partnerships and develop, as you guys all recall, during the pandemic, a lot of these assays weren't able to detect the virus at the beginning. So, right, people had no clue they were sick. And so what do? They send them all to the Frederick National Lab, up to my laboratory up in Frederick, and we were able to work very closely with the FDA. And with high-performance computing, we were able to analyze, develop standards, work closely with the WHO, the World Health Organization, to be able to put this into practice. And I was telling my colleagues up here on stage with me earlier that during the pandemic, the silver lining was everyone was combating, at least in healthcare, the primary enemy, which was COVID. right? There was no, this is mine, no one else can see this. Everyone was giving as much as they could information. That data was going into, our data storages. We were able to use that information to be able to make proper decisions about developing assays, developing standards, and standards that are being used today to allow us to have a normalcy again.
Oh, yeah, it's absolutely something. You didn't get a lot of organizations who were coming out pro-COVID, right? It was something we could rally behind.
Yes.
And I love that these answers here in terms of what we do at supercomputing. They're kind of what I've been accustomed to loving about this industry. But I really want to get to Shubho on this, because another thing we've been talking about at this show for several years is machine learning and artificial intelligence. If you ask me as an analyst, where are the worldwide greatest centers of excellence for AI? It's in some of the hyperscale companies. So Shubho, when you look at, from Meta's perspective, this HPC Accelerates theme, how does that apply to what you're doing at Meta? How do you relate to that theme?
Yeah, so FAIR's goal is to further the boundaries of AI. And AI, as we know, has been fueled by compute for the last 8 or 9 years. It is also an experimental field. So in an experimental field, you want to go through a lot of hypotheses really, really fast. And that means training and training fast. So if you have an idea, you want to close the loop from idea to writing code to training, and either discarding or going forward with a hypothesis. So for us, the reason we build these compute infrastructure is to essentially map out the landscape of innovation as fast as we can. And if in AI, if you look at the models tend to get larger, the data sets also are growing pretty fast. And in many ways, they're growing like 10x every 2 years or something like that. And some of the innovation that comes out of that, specifically out of large compute, is essentially large language models that can be used in many different areas. We have, especially, for example, in protein structure prediction. So we recently, I think, open sourced a 600 million database of protein structure from, it's called the Metagenomic Atlas. Came out of a large-ish, not quite the largest, but large-ish language model. We have been working on translation between 100 language pairs, so like 100K almost language directions for low resource languages. That also comes out of large compute infrastructure that we have. So for us, I mean, without compute, I would say AI doesn't even exist in many ways.
Jim, you were just talking about collaboration. Shubho's talking about open sourcing this protein database. You want to jump in? One topic that touched all of you going down the line was healthcare. Now, Jim, it's kind of an easy one for you. Do you want to build on what Shubho's talking about?
Yeah, no, I'd love to. So, one of the most difficult tasks we have in our group, in the research technology branch and in the Center for Human Immunology, is to be able to educate our clinicians and our basic researchers the benefit and the value of these databases. So a lot of times we'll find a lot of stuff like you shared with the databases where we have to build our own databases, curate those databases. For example, there's a lot of tick research going on with tick-borne diseases where our guys are working very closely to identify some of that open source information to be able to help curate so we can have some research discoveries that are going to apply at the clinical application, right? So I think one of the things you're going to clearly see, at least with the utilization of HPC, and this is something that we're working very hard on, the NIAID is offering so much funds in machine learning and AI, right? To be able to predict the next variant, to be able to predict the next pandemic, right? So being able to do that is going to be key to allowing us to prepare, right, as we move forward. The other piece I think is very important, I don't think we've talked a little bit about this, is training that next generation of young scientists, clinicians that are coming into the fields, right? Bringing those individuals in to be able to, the children today, this generation, I mean, different than my generation, I hate to say that, but they're just so attached with these little computers, right? And so it's interesting, we'll bring students in and they're able to do code and code in Python and things like that, which really help us to be able to advance their research understanding and then apply it at the clinical and the basic research arena. So we see it every day.
Jim and Shubho brought up two very important aspects of acceleration. The notion of strategic partnerships and cross-pollination of ideas. And we've experienced that in the Department of Energy and the Leadership Computing facilities through a strategic partnership with the National Cancer Institute and a strategic partnership with the Veterans Administration. These partnerships were built in a way that We respected each other's missions, but we advanced our respective science in a way that we could learn from each other. Yes. So the particular biomedical problem served as a grand challenge for us, bursting into exascale computing, and the biomedical community from the Veterans Administration or NCI benefited from state-of-the-art machine learning models.
Yes.
The unintended consequence of these partnerships, and I can speak to the NCI partnership, is that the models that we have been developing and deploying across the biomedical community, the AI models that are completely tailored to cancer clinical data, they found immediate translation during the pandemic in terms of leveraging these AI models with completely different data sets in terms of accelerating the search process of finding promising therapeutic targets. So these are some of the exciting things of partnerships and collaborations and cross-pollination of ideas that we often start with something in mind, and it can be so much more.
Yeah. And Gina, your point about the partnership with the NCI, one of the things we see at the NIH, and this is across all 27 institutes, is the mindset is changing, right? 20 years ago, it was get as many postdocs in the laboratory as possible and get as much data out there. Now these machines generate such a tsunami of data. It's what does this data tell us? You can wade through this information. What's the biological relevance to the disease state you're studying, right? And that's something we have to be able to apply, right? And so one of the things we've been able to do, and I talk about it, hopefully partner with you a little bit here, is being able to bring together what we classify as our integrated data sciences section, which is in the NIAID community at DIR, and be able to learn from the machine learning and AI and the capabilities you guys are applying and apply it to the biomedical research arena. That's key. That's key to success.
And this goes well beyond biomedical research. Shubho, you were talking about your natural language processing before, and you've got a project, No Language Left Behind. There's a lot of languages in the world.
Yeah, so one of Facebook's mission is connecting people, and we have 2 billion, 2.5 billion people using our services. And one thing we worry about is there are a lot of languages in the world, and many of them have very few speakers. Some of them are spoken only. So one of the projects that FAIR has been working on is No Language Left Behind, to enable translation between all pairs of languages for 100 languages. So that is a large effort. And from then on, we have recently done some research on languages that are spoken. For example, Hokkien is a widely spoken dialect in China, but it has no written form. So we are now going from NLP research for translation to what I think is multimodal translation, where languages that are spoken only, and then you can extend it to doing translation while you are speaking even. That's kind of the ultimate goal, which is exceedingly hard, but I think that's where we want to go to, where we really are connecting people who don't have a shared language on our platform.
Thomas, you were talking about national supercomputing centers versus serving humanity and what goes across borders on this topic of collaboration, whether it's healthcare or another domain. How would you expand on that?
So the scientific computing is about science, and science is a human heritage, is not a national. There is no national science. And so we had, for example, in Europe, starting with the medical field or the brain research, that had to go beyond anything we did in Switzerland or in any of the particular European countries, and where things came together with the Human Brain Project, that interestingly challenged us with exactly the things you've been talking about. We have on one side, we have data curation problems. We also have simulations. We have to bring these things together, and this was before the AI revolution, the recent AI revolution. And it pretty much prepared us to develop infrastructure at you can say, global or continental level, so collaborations, international collaborations, and I think helped even transform the way we see HPC infrastructures today. So when I look at our center, where we started when I took over 14 years ago, and where we are today, thanks to these collaborations in the neuroscience area, for example, or also in the Earth system science and weather, climate science area, where we are trying, in both areas, we are trying to tackle problems that humanity is facing, and they are pretty much motivating us to change the way we operate, we design and operate our facilities. And so I think you cannot compare where we are today to where we were just 10 years ago.
I agree.
When we talk about collaborations and changing the way things have been in response to human needs, I have to ask Jim about your initiatives with African Centers of Excellence for Bioinformatics and Data Science. Can you tell our audience a little more about those?
Yeah.
I was blown away by this.
So, and it really kind of aligns nicely with some of the collaborations as well. So as you guys know, NIAID has been doing a lot of this work in Bali, Sub-Saharan Africa, things like that, to be able to establish these bioinformatics centers, utilizing the national lab to put those things into place, because we can get those into place much more rapidly and more efficiently there. But the other thing we've also noticed now, and this is, and again, it goes back to Gina's statement earlier, which was the collaborations. Now the NCI is leaning towards looking at different types of cancers in these areas of Africa, right? Because one of the biggest problems that we saw, definitely during the pandemic, was to be able to get a good sample of the demographic of individuals in the United States, right? Cultural backgrounds, African American, Caucasian, Asian, Latino, right? What was the response? Each immune system is unique, right? To determine how we're going to respond to those individuals. So one of the things we've started to do now in partnership with the National Lab, the NCI is working very closely with NIAID to put those type of bioinformatics centers into place in Africa, not only for infectious diseases, but for cancer responses. So we're seeing that as well.
So when I look at collaboration in this, I could ask the broader question about how do your organizations work with other organizations to promote acceleration in ways that go beyond your own organizations, where you're combining resources or across regions or different skill sets or even spanning application domains.
So if you don't mind, I'd like to jump on that real quick. So one of the things we've done, and this is something we put into place about a year ago, one of my colleagues, a good friend of mine, who's the director of the Integrated Data Science section, Jack Collins, and I put together this vision about 10 years ago of building what we classified an informatics ecosystem, right? So one of the biggest problems we have is that you only have one or two informaticians, and there's tons of different biological questions that have to be answered, right? So what we put into place, and within a year, we brought over about 12 strong analysts, informaticians, that were able to do things from, next-gen sequencing analysis to structural biology, a little bit of AI, machine learning. But then what had happened is the other ICs started to buy into this ecosystem, where we went from 12 individuals, right? So now we have NIAID, NCI, NHLBI, NIDDK, NINDS, all have bought into this ecosystem now, where the IDSS has gone from 10 people to about 30 people, right? And the answers to the questions are so much easier because not one particular individual has all the answers, right? So if someone comes to me and says, hey, Jim, I want to be able to do X, Y, and Z, and I'm like, well, I don't know how to do it, but let me talk to Tom, because I think Tom knows how to do this. And he starts to build that analysis. So it just shares those resources. At the end of the day, it really allowed us to be able to move science forward much more at a rapidly rate. Because when you only have one informatician or one person that does a lot of the infrastructure and HPC, you're going to slow down. It's going to come to a grinding halt because those individuals get educated. So that partnership, and what we classified as the ecosystem, right? That ecosystem and sharing economy of scale, right? Sharing those resources, everyone is able to get their answers more rapidly, more efficiently.
This is why I love these conferences. I get you two next to each other on a panel and you're best friends already. I'm going to call Tom. We're gonna go partner. How do you feel about that? Get in there.
Well, going back to collaborations, what we have been forced by these problems that go beyond what you do in one country is we've been forced to react, not to think just about computing, but to think about the data sources, how to organize the data across different countries. And just taking it back to physical sciences, I don't know whether this has been talked about here in the US much. We have, for example, a square kilometer array and all the precursor projects that are going on in the southern hemisphere, so in Australia and in South Africa, where they set up these antennas, and where it is obvious that we have to combine the collection of data and then the processing of data and the analysis and the scientists who take interest in what information is in that data. And that's just to give you an example of a project that is set up from the get-go as a global collaboration.
And then others learning from what you guys put into place as best practices, so we can apply it to the next set of studies that are ongoing.
Yes, exactly. So, so things used to be, CERN changed a lot in how science is dealing with data analysis, and the whole world is coming together.
Yes.
There we had a single data source and a distributed analysis. And now we end up dealing with problems in many areas where the data is distributed, has new characteristics like veracity, velocity, that we have to deal with, variety, etc., that we have to deal with, and we are really learning in these collaborations. And what we also see, and I think this is where we, in the ETH domain, are very close to also what's going on in DOE and Office of Science, is that we have instruments like spallation sources or light sources, free electron lasers, that today are dealing with data volumes that you cannot manage as individual users anymore, and where the computing facilities that we operate have to collaborate and in designing the data analysis, etc., from the start.
Gina wants to get in. Go.
To continue Thomas's thread, since our worlds are very similar, for us, collaboration is a guiding principle for leadership computing facilities that are there to serve. And this collaboration with many different stakeholder communities, it starts with collaboration with the vendors, because we design and deploy jointly systems that are at the bleeding edge. We share the joy and the pain of the process. Then it is collaboration among the national labs that run such facilities, because we share practices, lessons learned, and how we can all benefit from each other. Collaboration among international entities through initiatives such as ADAG. And of course, as Thomas said, collaboration with different user communities, because each one of them has different needs. And if we truly want to serve, we need to be not reactive to these needs, but also proactive. Understand more deeply how their science, their scientific process evolves over time, and respond to these emerging needs. Just like the heterogeneous computational workloads that we have faced several years ago, the bread and butter of everything for us was modeling and simulation. And now we see modeling and simulation interleaved with large-scale data analytics and AI in so many applications. Great examples, the Gordon Bell submission.
Right.
Here's where the government and academic organizations are all in big agreement. It'd be easy to start to assume that, Shubo, you're at a big-time corporation, and yet you're also involved in a lot of academic collaborations for research.
Yeah, so collaboration for us as a lab inside of a corporate entity is a little bit different. So the way we like to think about ourselves is we have obviously some strings attached to the mothership, but we like to think about ourselves as an academic lab. So in any of the the geos that we operate in, so say the Bay Area or Seattle or New York, London, Paris, we have tie-ups with pretty much the leading universities there. So for example, with Berkeley, we have a formal program. We collaborate with universities in Paris to actually have students do their PhD degrees inside of FAIR. We have collaborations with UCL, for example. Many of the people who work at FAIR have come from academia, from the professors before, or they come as visiting researchers. So that's kind of one axis of collaboration for us. We don't obviously so much collaborate with the national lab, so to speak. The other axis of collaboration that has been somewhat successful is we have had a collaboration with NYU Langone Medical Center for doing MRIs 10x faster. So we open sourced a MRI data set, which I think has 6,000 brain scans and then 10,000 knee scans, one of the largest MRI data sets that's out there, quite successful. During COVID, we had a collaboration with the University of Vienna, I believe, to develop models for COVID spread. We had another one with I think the state of New Jersey for doing the same. And these were models that were used by the state to figure out like how soon are beds filling up, et cetera. And the third axis of collaboration is the frameworks and the code we develop. So we are very, very open source friendly. PyTorch, which is the leading framework in AI, actually came from FAIR. And there's several other frameworks that are quite popular in the field that had its genesis in FAIR and several data sets. So we really want to like make the technologies, the code, the model, the data set as much open as possible, which enables us to let the field grow much faster.
Well, let's spend just a minute talking about the balance there, though, because the flip side of collaboration is competition, right? And that certainly exists in different places. So it's one thing to sit back and say how great it would be if we could all totally collaborate evenly, and my data is your data and my resources are your resources. It's not necessarily realistic in all cases. What are the limits on it for your organizations? Where do you collaborate, but also where don't you collaborate?
So there is, we try to make data open, information open as much as possible. The achievements to advance in a certain area, there is competition. So competition is built in the scientific process. Also because you need different approaches, different ideas. And it's only when different approaches, different ideas come to see the same thing that you can really say it is reproducible and it is valid science. So the system is such that competition is built in the creation of it. In the end, the output, the knowledge that comes out has to be shared in the open. Yeah. At least that's what we are committing.
I echo what
I agree
Thomas
too.
says. Historically, competition and collaboration both fueled scientific research and productivity. You need competition to drive innovation. You need collaboration to accelerate it.
Yes, yes.
And we've seen that throughout the past few years with the pandemic. As Thomas said, you need new ideas. The way I translate that in my biomedical space, these new ideas, you need different hypotheses to be tested. And that's part of the competitive process. And that's what we still need to foster and encourage.
Yeah, yeah. And Gina, it's a great point. I mean, I can speak from my perspective as the Associate Director for Research Technologies is the goal here is a collaborative technological resource, right? But I think the piece that Gina and Thomas both hit on beautifully was we're consistently challenging our staff to come up with new ideas, to reach out and talk to individuals, to develop private-public partnerships, right? So we can bring those capabilities in-house that can help identify scientific discovery, clinical application, right? So you have to have that competition. Without competition, you really do become stale, right? And in our field, we can't do that, right? It's impossible. If you do that, you failed. It's over at that point, right? You cannot I mean, in 2 years from now, I could be up here again and talk about something completely different, right? Because we should be changing consistently. We got to grow.
Well, and that's what we do here, right, is chase new horizons. We're talking about the first exascale system on the top 500 list. We're talking about Facebook AI research, which is out at the forefront of AI and machine learning. I mean, we're chasing new horizons here.
So I think in the AI research, I find the field extremely collaborative. I mean, most of the code, idea, data sets are open. But I think one of the trends that we are seeing is training these really large models, and in these cases, if you don't have access to a large amount of compute, that becomes, it's a disadvantage. And I think the separation of industry and academia here, I think is a little bit troublesome because the top labs in the industry have so much compute that we can accelerate our ideas much, much faster than, say, you're an academic lab and you don't have access to that much infrastructure.
So Shubho, I thought that you were going to go down the different dimension we were discussing before, the unintended consequences of acceleration. Do we have too much of a good thing?
That's exactly what I'm going to ask here in a second. I'm going to make a quick note, though, that we are going to take questions from the audience, both live here in the room as well as online for those who are watching the stream and going through the online interface. If you have a question for these panelists, and I have a lot of them, so if you don't, I'll just keep going. But if you have a question, we have microphones in each aisle. You'll have to line up at those microphones. If you want to sit at your seat and raise your hand and yell your question from there, forget it. I won't hear you and we're not going to answer you. Go to the microphones in the aisles. I'll get to those starting in just a second. We'll also take questions online. I love that we're having this conversation. I was going to also get into the question of who owns all this data, but we already did ethics of HPC last year in this plenary, and we had a wonderful topic there. So I'll refer everyone to last year's conversation. But this one Gina just brought up, when you accelerate things, if you make the car go faster, you could have a bigger wreck. Right? Are there unintended consequences of acceleration? Are there ways that this could go wrong? You were about to dive into that, Gina, so I'll come back.
Well, I have struggled with this question, particularly in the context of AI, because I always joke that I'm old enough to have experienced the previous season of AI, and now it's another renaissance. It goes into cycles, and it seems that we're revisiting issues of the past, but now we are moving a lot faster than ever before. It is difficult to quantify acceleration of science. At least I don't know how to quantify that, but I believe that we all feel that everything moves a lot faster than ever before. And if we move too fast, I believe that we tend to harden our position with certain ideas, and we forget to apply the same level of scientific rigor that we would have applied if we were not under that continuous pressure of competition, innovation, and that competitive advantage. So how exactly we as a society strive for that balance? Because if you harden in a certain position, be it, for example, the very large language models, that's the magic bullet for everything, then we develop a lot of blind spots. So I would love to hear from you all your thoughts, but that's something that keeps bothering me with the narrative we have these days. Move, move, move faster. Are we asking ourselves, are we really going down the right direction? And how exactly can we do what Thomas said, more ideas at the table and do this hypothesis testing instead of betting on the next big shiny object?
Yeah, I mean, I don't have, go ahead.
No, go ahead, Shubho.
I don't have good answers, but they also kind of trouble me because right now in AI, there's a huge competition, typically of who can build the largest model. They're already in trillions of parameters that we can build, but they all kind of use the same-ish technique. So there's a lot of going down the same path of training larger and larger transformers. But if you look at radical ideas in research, they really come from the fringes. Yes. And I think I started doing AI in 2014 or so. And I think the diversity of models back then was much larger than what we have now. And that was really because we hadn't kind of found this one model that spanned multiple domains, so vision and speech where I used to work on, and language, all that very different kind of models. But nowadays, everything is really one large transformer, which, well, I'm glad the transformers are working and we can get more intelligence from data, but I'm also kind of sad that, is this it? Like, is this something beyond it? What is beyond it, and what is the idea in the fringe that we are not looking at? That would be, I think, nice for the field to kind of introspect and look at.
Thomas, were you about to jump in before?
You were asking about where we need to pay attention and what rec could we produce if we accelerate too much. And the part where we have to pay attention to is to make sure we bring society, we bring the people along with us. So if you accelerate too much, you end up losing the people. And we've seen it also during COVID, that it is very important that we bring the society along, and we do this by accelerating things they care about ultimately. And I think we have enough topics that around these questions of global warming, impact of extreme weathers on very sensitive infrastructure, etc., where we have to make sure that what we are accelerating and what we are developing, I strongly believe this, I said it before, has to remain in the open. The results have to be open, have to be challenged from all different sides, and we have to be open to the challenges. Very important to keep the trust of the societies, because if we end up losing that, we end up cheating, then we go down a dangerous path and into a wreck. So that's why I keep promoting this question of openness. And I'm sometimes a bit concerned how national politics or regional politics sometimes get into the way of this and try to build up boundaries for the sake of autonomy or misunderstood sovereignty.
Yeah. And I think to chime in what Thomas shared was, so from my perspective, our team is consistently sitting down with the basic researchers and the clinicians, and they're asking certain questions, right? And that for us is maybe we don't have that tool, and we classify it more as you guys would say, technology development, technology applications. And so what we spend a lot of time is, and I think I think you said this beautifully, Thomas, was we bring those clinicians, we bring those basic research along with us, right? So one of the things that our team will never do, at least in my branches, is they will not what we classify boutique computational sciences, right? They're going to spend time with the clinicians and understand how can we use this tool to bridge your scientific questions. So then you are bringing that society, at least from our field, the scientific society, along with us, and then having that application, right? So it's done together.
I absolutely love this topic, and in terms of bringing humanity along with us, it circles back around to the African Centers of Excellence that we were talking about before, bringing data science capabilities to Mali, to Uganda, where they didn't previously have the skills or the resources, and having that then be self-sufficient and sustainable going forward. But on the other hand, one thing we're tracking as analysts is an increase in nationalism around a lot of these supercomputing efforts, where we see here's an American effort, here's a European effort, here's a Japanese effort, here's a Chinese effort. We were hoping to have Dr. Hemant Darbari from CDAC and the National Supercomputing Mission in India on this panel. He unfortunately couldn't travel because he was pulled into meetings with the Prime Minister's office, but they're building a whole Indian national supercomputing infrastructure with domestic technologies. So, politics being what it is, there's that as well. We're not going to be able to plumb all of that on this panel. We do have a question out here in this aisle. I'll take that now.
Hello.
Yep.
Hi there, go.
I'm Elise Nedden from Nationwide Children's Hospital, and one of the things that I find probably most problematic currently and adversely affecting progress or acceleration of HPC is the proliferation of non-free software. So, like for instance, Cell Ranger and some of these bioinformatics programs that you get from vendors, they have like non-distribution clauses within their software, or people developing code in MATLAB or IDL, stuff of that nature. And then you get non-technical users who don't know how to port that software, or they're kind of just stuck, right? What kind of strategies do you see getting past those types of barriers?
Sure. I'm going to restate a lot of what you just said because the online, it's hard to hear the microphones out there. So the question was about proprietary versus open source software and what strategies there are for increasing portability and access for more people to software, some of which might be proprietary. Now, this relates to something we were talking about before, which is you put something out there and then you have to sustain it as well. So why don't we dive in on that?
So proprietary software doesn't work.
I'm sorry, proprietary software doesn't work?
Doesn't work.
There are a lot of commercial software companies who exhibit here.
Yes, so the best example we have is with, Unix disappeared and was replaced by open source free software. And so ultimately, the software models that scale and lead to reproducible results have to be open. And I think this is something that has been proven now over the decades that I've been in the business, and I have a few white hair now. So I've been there for some time, and I think the same applies to ultimately to data and results that come out of the research. And it's only when we trust, we can be open, and I'm not saying open from the very first moment on, but we have to have a system that forces us to become open. Then we can trust each other, and we can trust.
So
we
that's
can also
one
gain
vote
the trust
against
of the
commercial
society.
software. Anything else on the panel?
And commercial software is open. What they do in the hyperscalers also is open.
Yeah, I can kind of, so in AI, a lot of the software is open, thankfully. But I think one of the trends, the stuff that is not open are the drivers and the firmware. And I think going forward, my hypothesis, and this is my personal hypothesis, is you're going to see firmwares getting more and more beefy. And that stuff will never be open, I don't think. So this is a trend that I think we are going to increasingly see, which worries me somewhat, but I don't know what the solution is.
Gina, were you about to say something on that, or do you want to pass?
I thought the question was going towards what we are doing or we need to do as a community in terms of software sustainability. Because there is one aspect in terms of proprietary or open software, but what do we do to sustain software for the long run and enable the users to grow with it? And this is certainly a topic that attracts a lot of discussion within the Department of Energy, considering the huge investments that have been made into the exascale computing project, with a lot of software that has been developed to enable the scientific community, including the biomedical community with the cancer application. So how we make critical decisions of what software we sustain and for how long, that's actually part of a conversation that we need to have as a community, because that requires substantial resources.
I'll say for me as an analyst, sometimes I like to just argue the other side of the equation in favor of commercial software. I think there are plenty of scenarios where you're offered free software and you think of it as being like free ice cream, and you need to think of it more like a free puppy, right? It requires a little bit of maintenance with it as you go along.
Good point, yeah.
So I think there are multiple sides to this. Let's take this question in this aisle over here. Thank you.
Hello, my name is Ryan. My question actually has to do with the lockdown of COVID data at the beginning of COVID in 2020, where we saw several proprietary groups performing private research. As with all things on the internet, it got shared, and then lawsuits started going out, and eventually it was decided that all COVID data would be open for research, at least to some degree. I was wondering 2.5 years later what you guys think of this. And if you, this is a very political question, but if you could do this to any other data, what would it be? I'm very curious about your guys'
All right,
answer.
this is going to be a good question for Jim to start off. Early COVID, there was open data, then there's proprietary data, then we said we had to share data. Let me rephrase this in terms of lessons learned, and should those lessons be applied to other data beyond medical data? Go ahead, Jim.
Well, so to make sure I understand your question correctly, I think at the beginning, a lot of that data was not shared because a lot of first of all, we didn't know who had COVID and how early it was here. So, and those individuals were not agreeing to have that information shared, right? So a lot of it, I mean, HIPAA law is a lot, that's just the way it works, right? As we progressed through the pandemic, and there was a lot of changes, as you guys know, went from Delta to Omicron, the different variants, there was information that we had to gather from that, right? And be able to understand what were the different types of immune response. Is it a cytokine storm? Is it something with the adaptive immune system, the innate immune system? Is it something to deal with perspective of long hauler syndrome? That's where we're at now, where we don't understand enough about the virus to know what the long-term effects are on the virus, on the individual, right? What's the immune system doing that's causing these individuals to have, you know, a series of upper respiratory infections, heart issues, right? Different responses from the ACE2 receptors, right? We don't know what those are. So a lot of information did become public because we were trying to be able to understand better what this virus did to the individual, right? And you really got to think of it, and I think the most easiest way to look at this, and I'll tell you a funny story. I was sitting down with one of our colleagues at NIAID, Dr. Yasmin Belkade, who's a card-carrying immunologist, and someone that does a lot of cancer. Myself, I really understood this, and it made sense, was every individual's immune system in this room is unique, right? So you're all going to respond differently to the vaccines. You're going to respond differently to the infection. It's the same thing with cancer, right? Back in the 90s, people were just dosed with the same type. If the cancer looked like this, everyone got the same drug. Now, if you know, Addison has a different receptor that's mutated, we don't want to use that class of drugs, so we want to use a certain drug for him to have a better response. So the data being shared now is to be able to get enough information out there because we are, and I hate to say it, we're going to see some issues in the long hauler components of COVID. It just is what it is.
I have a slightly different view on this,
Okay, go ahead,
particularly
Gina.
when it comes to biomedical data. Data sharing in the biomedical space remains for me a deeply administrative and policy constraint.
Yes.
And every time you have policy-related issues, they move incredibly slowly, and technical solutions are easier to get than policy solutions. I think what the community has been doing in the past few years with solutions such as, you know, privacy-preserving computing and federated learning were inspired exactly by this. How long can we wait to break down the silos, the data silos? And we have even more constraints in terms of combining international data because the policies in Europe are stricter than the policies in the US. So I would love to see our HPC community to work more methodically on finding solutions in the space of privacy-preserving computing and federated learning. They're not going to be optimal solutions, just like the identification of data that the NIAID does is not a foolproof solution, so that we can keep moving. The whole debate, we need to break down silos. How many decades are we talking about this?
Well, and I love that this topic came up. Thank you for the question. It links directly to a question that came in online that I want to hit, and I'll come over there to that aisle in a minute. But I checked the online questions. There's one that's getting upvoted more than any other, and reading the question, I completely agree. You were bringing up policy. Now, we're not politicians here, But talking about something like climate change, we can do all the models, or COVID or anything, but if you have national policy that just says, well, I don't like that, I'm going to go a different way, right? What role does HPC have in accelerating essentially social thought or social change in the face of, say, disinformation campaigns or people who don't want the science to be the way that it's pointing? Any views on that? We didn't rehearse this one in advance.
Okay.
Whether this is climate change or something to do with the pandemic, in the end, you need a system that respects the individual. And you know, you've been critical of the European policies on data. I think they are built on the basic idea that we have to respect the privacy of the individual and value the individual. And at the same time, I think the policies in pretty much all European countries I know of, in Western Europe, is that anybody ultimately is accountable to the people. We actually have this also in this country. We sometimes forget about it, particularly when we start splitting into a bipartite system, which is unfortunate. So if we have a system that is accountable to the people and that is valuing the individual and not overruling and reducing the individual to data, then we are on the safe path. If you deviate from that, and this doesn't matter in which area, then we are always going down a dangerous path.
I'll say this from my perspective.
And again, you can take science, and this is where HPC is rooted. This is the idea of science going back to, you can say, Tycho Brahe and Galilei and the basic ideas on how you get knowledge.
And I'm sorry, Gina, you were about to say something. You go before me.
So Thomas, I mean, accountability is very important, but respecting the individual also means empowering the individual to make decisions about how their data will be used. And I do believe that we live in a very different era where we are far more open with our life on a day-to-day basis, and then we feel that, you know, this is my private data, nobody should be touching it. In the biomedical space, there are benefits for sharing and sharing broadly. But yes, there always can be actors that will use the data the wrong way. But under the proper data use agreements, I do believe that we can move forward. I mean, I've seen how it has happened with the DOE NCI partnership, where when we started, everybody thought that there is no way that there will be data use agreements because the registries, the cancer registries themselves, were not sharing data with one another. But we reached the point where they do share data, we do compute at that level, and they reap the benefits of AI tools that are only to be shared with them, because they are the data owners, therefore they own and the products of this research. So there are models of collaborations where we can open the aperture of comfort in terms of sharing. I'm not saying broadly sharing with everybody else. I feel actually more concerned with all of these de-identified data sets that exist out there, because I don't believe they're truly de-identified, and there are plenty of studies that have demonstrated that you can do reverse engineering. So there are technical solutions that we should be deploying with the proper agreements.
Coming back to the policy
of the right conduct.
Coming back to the policy question, I'll give my view as an industry analyst and market researcher. I think the essence of the thing is that science itself doesn't have a political agenda. Science is science. Now, a scientist might have a political agenda, right? And, and if I went into market research trying to prove something, no problem, I'll prove whatever you want. If my goal is to prove that the vast majority of this audience is left-handed, I can put together a study to prove that. It won't have a very good methodology. In fact, it'll be very easy. If I've already decided in advance what I want the answer to be, I'll prove whatever you want, right? But, and that goes to science too. If you're coming in with the answer made up, you don't have to do very good science in order to prove it. And sometimes, you know, the good, careful science that goes down the middle that's complicated can get lost behind loud messages that people are trying to say. I think we do the best we can at this conference to represent unbiased science, but there are going to be biased scientists out there sometimes. So, very quickly, because I want to get that other question.
Biased scientists will be called out by the system.
Hopefully.
And I think this is what one of these online questions was about. If we lose the culture that pretty much is agreed upon in physical sciences, that there is a way how we as subjective human beings can find agree on an objective reality, can actually agree on facts. And there are systematic methods that science, natural science, teaches us how we can get there. We have to absolutely make sure that we don't lose them, these methods, so that we can call out those people who can try to prove
Let's get this other question
and create their own facts, which you can't.
Thank you, Thomas.
And then you're fooling yourself if you think you can.
Go ahead.
My question's really along the same lines. I mean, the notion of a crash, because we're accelerating so fast and leaving the people behind, is being brought up again and again here. And I'm newer to supercomputing in general, and I've heard these two words pop up a lot, which is the reproducibility crisis come up significantly, where one data set run through an AI model can produce one result, and through another model creates another result, and how do you agree which model is more true? It just becomes a black box where you can't verify the methodology of things. And it happens in supercomputing as well, where one simulation can run on one supercomputer that's based on one architecture, one compiler, and then run again on another supercomputer, and you'll have a different result. So, like, how do the reproducibility crisis doesn't really sound like reproducibility, it sounds more like a trust crisis when it comes to experimentation and verification. And I think that ties back in.
I think that's an excellent question. Essentially, is how do we build trust in HPC? You do these simulations. It could be a very high fidelity simulation, but the question essentially is how do you get people to believe the simulation, particularly if it's something that you're not going to physically measure, whether it's a 100-year climate forecast, it's going to take a while to measure it out actually physically, or something like a nuclear explosion that you're modeling, but you don't actually want to test against reality. How do we build faith in the simulation?
So I heard two different things. I heard you talking about reproducibility. You're talking about validation.
That's true, both, yes.
Yeah.
Right? So when it comes to validation of complex physical models, without being part of that community, Thomas may speak to that, I understand that the validation is done with retrospective data, right? Validation. Now reproducibility is a different thing.
Okay, so reproducibility is the foundation of being able to do to even talk about science. And clearly we have, I think probably any time there are new mathematical methods being developed, numerical methods, scientific methods, they have to be challenged. And you face the problem of reproducibility. But without reproducibility, you're not, and without that goal, I don't even see how you can validate anything, okay?
It's
So you
the
need to be
validation of
able
the
to do
individual
something
model.
over and you need, different people need to be able to see the same thing. Otherwise, it cannot be valid from a scientific point of view. It can be, you know, it can be a belief. Every one of us can have our own, will have our own belief, our own subjective views. But when we do something scientifically, we have to start with understanding how others can reproduce it. Then comes
You
the
looked
next
like you were going to
question,
respond to that.
where we have to talk about validation. And again, there is no science, sorry, natural science without
Okay.
validation.
So in the biomedical space, when we talk about reproducibility, there are two types of reproducibility. Either I try to train a similar model with my own data because I don't have access to the sensitive data, yet that model doesn't work in my own population. That's one kind of failing reproducibility. The other, the most standard way of reproducibility, I take the same code, I take the same data set, and I try to run it in my own computing environment. I don't get those results. So these are two different aspects when we talk about reproducibility, and we need to differentiate those two, especially since, Addison, you said, what if you run it in your own HPC environment, right, versus another HPC environment? Reproducibility is very important. We know that the scientific community has made great progress. There are new policies, regulations. Anywhere you apply for the typical federal funding, there is a requirement of reproducibility, and that requirement becomes extremely difficult now as we talk about AI models, right? And how you initialize the models and all of these things. The unintended consequence, to go back to reproducibility, is that often the more complex these models become and the more computational resources they require, this is a huge burden for a scientist to do reproducibility. So to me, that comes back to the resources. We, as a scientific community, as a nation, as an international community, we need to think that if we indeed care about software sustainability, if we indeed care about reproducibility and validation, we need to put resources behind that. We cannot leave this to the academic scientists that try to do a lot more with fewer resources than they had.
Your comment about community is a perfect segue to the end of the panel. I'm sorry we're out of time for audience questions, because one of the most exciting things about SC22 is that so many of us are back together as a community as we're talking about HPC Accelerates. So as we're just starting the conference now, as we accelerate into the week ahead, each of you take just 30 seconds and tell me, what are your big goals for your organization now, and how does that relate to getting together as a community at SC22? Go ahead, Jim, and we'll just go down the line.
Sure. So from my perspective, it's to be able to identify the different tools, resources, and collaborations that we're going to be able to apply to the healthcare biomedical field. And how can we bring that back to the NIH to help address some of the scientific discoveries, clinical applications, anything from vaccines for cancer to different types of therapeutics for tick-borne diseases is really what I want to look at.
Thomas.
Well, one of our immediate goals or concerns is to be able to go back and solve the problems as scientists we are called to solve for society and humanity, and in particular overcome some of the political barriers that have been set to us, because we are working on problems that we all have to deal with, and we have, I see this more and more, and it is really worrying me, politics, national politics that is coming in our way and excluding things like the exclusion of Britain from Europe, for example.
For me, selfishly, I work on some of the stuff that Gina touched upon in private computation and in doing compute on data that is encrypted. And that is, I think, is actually the ultimate HPC. Like, we need 1,000 to 1,000,000x more compute to do anything in the private domain. So for me, in the week that is coming up, trying to see if there are other people who are working in a similar space. And for lab as a general, like we are a huge consumer of HPC and it really accelerates the research. So taking back ideas or like on vendors or products on the show floor, that will help us do that. That's the second objective for me.
Gina, this is more than just a victory lap for you.
Well, it's very easy for me to say that our big goal is, of course, to deploy Frontier to the scientific community in the beginning of 2023, to engage with the broadest scientific communities that can make the most of the resources, to work with them, to help them make the most of this tremendous strategic instrument of science. And a personal target for me moving forward with this facility, I would like to see OLCF leading the charge towards energy efficient HPC. That's a cultural shift for the HPC community, but it is our social responsibility to take those steps.
Well, I could talk to you for hours. I mean, this is exactly what I'm here for and why I'm so glad we're together as a community. Unfortunately, we're out of time. I have been thrilled to be able to moderate this panel. I'm really looking forward to the week ahead. I would really like to thank the SC22 Steering Committee for getting us all together in Dallas. I'm very excited about the week ahead. Thank you for attending this opening session. I'm looking forward to interacting with all of you throughout the week. And please join me in thanking again my panelists, Jim Cherry, Thomas Schulthess, Shubho Sengupta, and Gina Tourassi. I pass it back to Rupak Biswas, who's the panel's chair. Thank you. Thanks, Jim.
Wow. Thank you, everyone who attended this insightful panel, and especially our moderator and speakers. I invite you now to go enjoy the SC22 opening gala in the Convention Center's exhibits hall starting at 7 p.m. And by the way, the ribbon cutting is at 6:45, and I hope to see all of you there. Thank you.